Hey, hi everybody. Very good evening and happy Pongal to all of you. Right, and someone of you will be celebrating Makar Sankranti also. Yes, come Sunny, good evening. Makar Sankranti also, so happy Makar Sankranti, happy Pongal, whichever one you're celebrating. I see that there is less strength today. I don't know why. Okay, fine, no issues. We'll start. We'll start the class. Let me share my screen. Right. So last class, we have been solving problems on Graham's law of diffusion. There's a few formulas which you have to know, right? We saw how to calculate the rate of diffusion, if you can remember. Then we actually solved some questions based on this bulb, right? So, but we didn't do any problems on ideal gas equation yet, or say any other laws yet. So today we'll start with this problems on ideal gas equation, other laws, and then we'll move on to the next topic, right? So people, get ready. Get ready with your pen and a paper or notebooks, right? So we are going to start. Okay. So problem number 1. Please take note. If 500 ml of a gas, if 500 ml of a gas is compressed, right? If 500 ml of a gas is compressed by increasing its pressure, and I hope you're all taking down. Please take on the question, people. Right? If 500 ml of a gas is compressed by increasing its pressure, by 10%, by increasing its pressure by 10%, find the final volume. Find the final volume. Okay, I'll repeat the question, people. If 500 ml of a gas is compressed by increasing pressure of 10%, right? They're asking you find the final volume. Go for it.
So, is there anything about temperature?
Sorry?
Is there anything about temperature?
No, our temperature is constant. Okay, when they don't tell you anything about something, that means it is constant. Okay, by default. So we know this question is obviously from Boyle's law, right? Because pressure is changing, volume is changing, and the temperature is kept constant. So you have to know, it is just pure mathematics, right? You have to know how percentage works.
Sir, 450 ml.
Sorry?
450 ml.
Yeah, approximately 450 ml is the answer, yes. Right. So it's very simple, people. All that we have to use is P1 V1 equal to P2 V2. This is what we have to use, right? Now the initial volume is given. V1 is given to be 500 ml, and pressure is not directly given to you, right? But I'll be able to do something with the pressure, right? Say initially the pressure was P1. This is your initial pressure. right? This is your initial pressure. What are they telling? They are telling that the final pressure, right? The final pressure is actually 10% higher than the initial pressure, right? 10% higher than the initial pressure, right? So now can I write it like this? It is equal to P1 plus 10% of P1. Is it not, right, people? P1 plus 10% of P1, right? Okay. So now how do you do this? So P2 is equal to the initial pressure plus 10% of it, right? It is increased by 10%. That's what they say, final pressure, right? So can I write this as P1 plus 0.1 into P? Now, how do you convert this percentage into like this? This is very simple. 10 by 100 into P1 is what is represented by this percentage. Okay. Whenever percentage is given, you divided by 100 and you're going to get the actual value. Okay. Right. So 10% of P1 means 0.1 P1. That's it. Very simple. Right. So what is the final pressure now? The final pressure P2 is nothing but 1.1 P1. Very simple. P1 plus 0.1 P1 will become, this is 1 P1, right? Plus 0.1 P1 will become 1.1 P1. That's it. That's it. You have to substitute in the values and you're going to get the answer. So P1 is the initial pressure. V1 is 500 into 500 is equal to P2 is now 1.1 into P1, sorry, 1.1 into P1, and the volume V2 is what we have to find. So P1 gets cancelled. So all that we have is volume is equal to 500. That is final volume is equal to 500 divided by 1.1. Approximately, like, exact answer is 454.5 ml. Right? This is the exact answer you should be getting. Right? Very, very simple. In terms of percentage, if we give you, yeah, tell me.
Sir, can we say that if pressure is increased by 10%, then the volume should decrease by 10% in order to keep it as constant?
Yeah, we can say that. Yes, yes. That is also a good idea. Right? If pressure is increased by
Sir,
10%.
but then using that, we get 450 ml exactly, right?
Yeah, 450 ml you'll be getting exactly. But again, okay, why is it not working? You'll be getting exactly 50%. I mean, 10% of this thing would be 50. So we'll be exactly getting 450. Right? But why is it not working? Okay, let me check this. It should be ideally working, right? Why is it not working? Pressure is increased by 10%, so volume should decrease by 10%. Makes sense. I'll check it. Okay. Approximately, you're getting the same answer, but again, not the exact answer. But I would prefer to go in this way only. Whatever the way I have solved the question, I would prefer to go in this way, but I'll clarify this. Why is it not working like that? 10% increase means 10% decrease.
Sir, sir, I think I got it. Like, pressure and volume are not equal, right? So they can differ, like they can vary with how much ever amount. So we can't say that if pressure is increasing by 10%, then volume should decrease by 10%.
Makes sense. I'll give little more clarity about this. Okay, maybe after the break, right? I'll give little more clarity about this. Why is it like this? Okay, fine. Next question coming to you. Okay. So question number 2. Take down. An open empty container. An open empty container has a volume of 2.05 liters. Has a volume of 2.05 liters. Okay, an open empty container has a volume of 2.05 liters. Okay. Fine. It is kept at a temperature of 5 degrees Celsius. Already, right? Like, it is initially kept at a temperature of 5 degrees Celsius. It is initially kept at a temperature of 5 degrees Celsius and is now heated to 21 degrees Celsius. And it is now heated to 21 degrees Celsius. Right? Now the question is, calculate the volume of air. Calculate the volume of air that will escape the container. Calculate the volume of air that will escape the container. So I'll repeat the question entirely one more time, people. Right? An open empty container has a volume of 2.05 liters. Okay. It is initially kept at a temperature of 5 degrees Celsius and is now allowed to, and it is now heated to 21 degrees Celsius. Right? And the question is, calculate the volume of air that will escape the container. Right? Think about it. Now remember, that's an open container, not a closed container, people. Right? So definitely the gas can escape. If you heat, if not the gas, the air is inside can escape, right? Because it's an open container.
Sir, 6.56 liters.
6.56 liters. Now the initial volume itself is only 2.05. Right? Yeah, it can increase, but that much increase. Okay, what law is this? We understand that this is Charles' law. People, right? Then what is the equation for Charles' law? Say we can write V1
Sir,
by
V upon T is constant.
V1 by T1 equal to V2 by T2. This is what we have to use, right? So we know all the temperatures, all the pressures, right? But remember that temperature has to be substituted in terms of Kelvin, not degrees Celsius. Please be very careful in these kind of questions. The question they have given to you, given the temperature in terms of degrees Celsius, you have to convert it in terms of Kelvin, then only do the problem. Right? Now let us check what is going to happen. Right? Now we are not, this volume we are mentioning is not the volume of the container, rather the volume of air inside the container. Okay, volume of air inside the container. And remember that the container cannot expand. Okay, it's a very rigid container, it cannot expand. Right? Okay, keeping all this in mind, we can just substitute the values. Right? So initial volume was 2.05 liters and the initial temperature was 5 degrees Celsius. So 273 plus 5 will become 278 Kelvin. Okay, 278 Kelvin is what was the initial temperature. V2 is what we have to find, right? And the temperature T2 is now what? 21 degrees Celsius. So 21 will become 294 Kelvin.
Yes.
Okay, right. Now, if you do the calculations properly, now the final volume of the gas, please understand the final volume of the gas is, you will be fine. You'll be able to find out. How will you find out? That will be
around 2.16.
Yeah, correct. Right. So you'll be able to easily calculate that. So it will be this into 294 divided by 278. So final volume of the air, you will find it to be 2.17 liters. Right now, but please understand, people, the capacity of the container is only how much? The capacity of the container is only 2.05 liters. But now the gas is expanding, or say the air is expanding to 2.17 liters. Right. So whatever is the extra thing which is coming out, that is the one which is going to escape, because that will not be there inside the container. The container can occupy only 2.05 liters. Right. But the air is now getting expanded into 2.17 liters, which is greater than the 2.05. Right. So I can tell the volume of air escaped would have been the difference between these two, right? 2.17 minus 2.05. Right. So you will be getting the answer as 0.12 liters. This is the volume of air that escaped when I heated the container. Very, very simple. Okay. This volume, whatever you're finding, is the volume of the air finally. Right. But that you see that it is greater than the volume of the container itself. Obviously, the container will not be able to hold it. Right. So obviously, whatever is extra, that will escape. What is extra? The difference between them is what is extra. That comes out to be 0.12 liters. Right. I hope everybody is. Yeah. What is it?
Sir, but since the container is open, we can't say the volume of air to be fixed, right?
Volume of air will?
To be fixed, right?
Yeah, exactly. Volume of air is fixed. Right. So if at all I assume, like say, this particular calculation, whatever you're doing here, right, is assuming the fact that there is, they say the container can increase its shape. The container can increase its volume. Right. And if that's the case, the container of the volume should be this much, 2.17 liters, then only it can actually occupy, I mean, that can accommodate all the gas. But no, the volume of the container will not be able to increase, right? So whatever the extra volume of the gas is coming, right, that will eventually try to escape. That's it. That's all. That's how you see this question.
Understood, sir.
Okay, right, good. Next question coming to you. Okay, let me search for a good question. Right. The problem, right? Take down. A gas kept in a closed vessel. A gas kept in a closed vessel is heated by 1 degree Celsius. A gas kept in a closed vessel is heated by 1 degree Celsius. Full stop. During this process, the pressure of the gas, increases by 0.4%. The pressure of the gas increases by 0.4%. Okay, right? Now the question is, calculate the final temperature. Calculate the final temperature. All right, I'll repeat the question one more time. A gas kept in a closed vessel is heated by 1 degree Celsius, and during this process the pressure of the gas was increased by 0.4%. right? Now what you have to find? You have to find the final temperature. Calculate the final temperature. Now please understand, the initial temperature is not 1 degree Celsius. Please understand, it is heated by 1 degree Celsius. So whatever was the initial temperature, 1 degree Celsius rise. That's what you have to understand. It's not like it is some temperature, it is now 1 degree Celsius. No. What, say if it was, for example, if it was 100 degrees Celsius, now it is going to become 101 degree Celsius. That's what you have to understand, by heated up by 1 degree Celsius. Okay. But if I say heated to 1 degree Celsius, that means what? Now the temperature is 1 degree Celsius. Yeah, that small word change will actually change a lot of things in the question. Now they're saying that it is heated by 1 degree Celsius, means there is an increase in temperature of 1 degree Celsius. Okay, go for it and tell me what you get. Okay, so literally no numbers are given to you, only percentages, how much is increasing, all those only given to you people, right? Think about it. So here obviously you have to use Gay-Lussac's law. Right? Because it's about temperature and pressure.
Sir.
Yeah.
Sir, I'm getting answer is 250, but I don't know the unit. Is it Kelvin or degree Celsius?
450, okay.
No, sir, 250, 250.
250, okay. That was the initial temperature or final temperature.
Oh, sorry, sir. That was the initial temperature.
That was the initial temperature. So final temperature should be
251.
That's it. That's in Kelvin only.
Same answer.
Yeah, the answer is correct. Okay. So people, very simple. So we have P1 by T1 equal to P2 by T2. Done. Right. So again, let me tell that the P1 was the initial pressure. P1 was the initial pressure. Right. Now what are they telling about the final pressure? The final pressure is P1 plus 0.4 percentage of P1 plus 0.4 percentage of P1. That's what is given in the question. It is increased by 0.4%. Right? Okay. Now how can I write this? I can write this as P1 divided by 0.4 divided by 100 into P1. Sorry, divided by 100 into P1. Right? So that is nothing but P1 plus 0. Already. So 2 more points. 0.004 P1. Right? So you will be getting how much? P2 value as, can I write it as 1.00, no, only 2 zeros for P1. That is the final pressure now. Okay. Now go to the equation, right? And also I can write one thing. This T2 is what? T1 was the initial temperature, right? Now they're telling that the gas is heated up by 1 degree Celsius. So I can also tell that the T2 is 1 degree Celsius or 1 Kelvin. Now please understand, 1 degree Celsius or 1 Kelvin, the what to say, the scale is same, right? Don't worry about it. Okay, so we have it is increased by 1 degree Celsius or 1 Kelvin. You're gonna get the same answer. Okay, right. So this is how we can talk about T2 and T1. Right, that is also okay. It is given in the question. Now substitute all the things which you know, right? So P1, let us keep it as P1 only. T1, let us keep it as T1 only. Now T2, what happened to T2? It is 1.004 T1 divided by, now T2 I know is nothing but T1 plus 1. Done. So T1 gets cancelled. So what we have T1 goes here, T1 plus 1 is equal to 1.004 T1, right? So I think I'll be able to do this, right? So all that you'll get is 0.004 T1. If I bring it this side, you'll be getting it as 1. Okay, right? If you bring this T1 this side, this is 1 T1, 1.004 T1 minus T1, that is 1 T1 will give you 0.004 T1, that is equal to 1. And if you get T1 as 250 Kelvin, okay, you'll get the T1 value as 250 Kelvin, but that is not the answer, people. What is they asking? This is your initial temperature, T1. Final temperature I know is T1 plus 1, that is nothing but 251 Kelvin, and this is the answer to this question.
Sir?
Yeah, tell me.
Sir, so in all the laws, the temperature is in Kelvin?
Yeah, in any of the laws, any of the thing, wherever you substitute temperature, not only in this chapter, any chapter for that matter, it is always going to be in Kelvin only. Okay,
sir.
All right. Good. Next question. Fine. Okay, another question, people. Next question. Fourth question. Okay. Temperature of a gas is T Kelvin. Okay, T is the value and Kelvin is the unit. Okay, right? This value is known. Okay, assume that is a number which you know it. Okay, T is a value which you know in the question. It's given in the question. Okay, right? Temperature of a gas is T Kelvin. Okay, now they're asking calculate the temperature at which both the pressure and the volume are halved. Right? Calculate the temperature at which both the pressure and the volumes are halved from the initial value, obviously. Right? Halved from their initial value. You can take it like that. This is a little tricky, okay? But I'll let me see, like if you're able to do it. So you have to get the answer in terms of T. Okay? In terms of T. So people, the clue I can give you is that you have to combine 3 laws. You have to combine Boyle's law, Charles' law, and Gay-Lussac's law and get an equation. Not the ideal gas equation, okay? This is not the ideal gas equation because there the number of moles also come. Avogadro law is also included. But in this case, no number of moles, nothing you're talking about. Okay? So the clue is that you have to combine 3 laws, that is Boyle's law, Charles' law, and Gay-Lussac's law to get an equation. Okay? And that equation is a solution for this question.
Sir, is it T upon 2?
Sorry,
T upon 2, half.
T upon 2? No. Any other answers? Okay. So people, the equation which you have to use, as I told you, you have to combine three laws because volume is changing, temperature is changing, and pressure is changing. All the three are changing, right? So we have to combine these laws to get this particular equation. P1 V1 by T1 equal to P2 V2 by T2. Very, very simple, right? We know P1 V1 equal to P2 V2. T1 by T1 equal to P2 by T2. V1 by T1 is equal to V2 by T2. Everything we know. Combine all that, and this is the equation we have to work with. P1 V1 by T1 equal to P2 V2 by T2. All right. Okay. Now P1, okay, initial pressure, right? Now what is happening to P2? It is becoming half. P1 by 2. Okay. Same way, V1 is the initial volume. Okay. Now what is happening to the final volume? The final volume is becoming half of the initial volume. Okay. Done. Now the initial temperature T1 was some T degrees or T Kelvin. Okay. We have to find what is T2. This is what we need to do. Very, very simple question, right? So if I do that, let me substitute P1 V1 by T. Okay, the T1 is nothing but some small t Kelvin. Okay, now P2, what is happening? It is becoming P1 by 2 into and the volume is also becoming V1 divided by 2. So this whole thing divided by the temperature T2. This is what you will get. Okay, so P1 V1 gets cancelled, right? So can I tell T2, right? You will get it as T, which is the known value, divided by 4. That is the final temperature. Kelvin.
Sir.
Yeah.
Sir, but if we combine, technically, shouldn't we get P1 V2 by T square?
Sorry, what are you telling?
Sir, if we combine all the laws, technically, shouldn't we get P1 V1 upon T square equals P2 V2 upon
P1 V1 upon T squared. No. If that's the case, then the same thing should happen for ideal gas equation also. Right? So, like, it's like, you know that, see, what does this indicate is that PV by T is constant. That is all you have to understand. Right? Now, what, like, this combines all the three laws basically. Pressure is inversely proportional to volume, pressure is directly proportional to temperature, and volume is directly proportional to temperature. That's it. Is it like volume is directly proportional to temperature squared? Then maybe that the powers will come. Now we have only one linearity. All the things are linearly connected. There is no other powers. Okay.
Sir, so why isn't this a law?
Why is it?
Why isn't this a law? Like some law.
Why isn't this allowed? Because that's what the law says, right? Because they say that they are either directly proportional. The law doesn't say that P is directly proportional to T squared. If it has told, yes, right? But it doesn't say that. It just says that P is directly proportional to T, V is directly proportional to T, and P is inversely proportional to V. That's it. You just have to combine.
No, sir, I meant why isn't PV upon T equals constant a law?
Why is it allowed? Why it is allowed, right? PV upon T is constant. Yes. It is allowed.
Okay, sir.
That's what you're doing, right? PV upon T is constant means what? Whatever be the product of P and V divided by T, that particular volume, temperature, and pressure, that all the other things like P1 V1 by T1 equal to P2 V2 by T2, so on, so forth, whatever, everything will be equal to one constant value. That is understood. Yes.
Okay, sir. Understood.
Right? So we get T2 is equal to T by 4 Kelvin. That's it. Very, very simple. Only one equation extra. P1 V1 by T1 equal to P2 V2 by T2. Done. Right? Okay. Next question. Okay. Let us do some interesting question. Okay. These are all are little easy, like comparatively, right? Okay. Let us do this question. Okay, fine. Take them. A spherical balloon, this is fifth question for the day. A spherical balloon of 21 centimeter, 21 centimeter of diameter. A spherical balloon of 21 centimeter diameter is to be filled with hydrogen gas, is to be filled with hydrogen gas at NTP. Okay, I don't know whether you have heard this term NTP, normal temperature and pressure. Okay, right. So a spherical balloon of 21 centimeter diameter is to be filled with hydrogen gas at NTP from a cylinder containing H2 gas, from a cylinder containing H2 gas at 20 atm, containing H2 gas at 20 atm and 27 degrees Celsius. Okay, right. Now they're saying the cylinder can hold, the cylinder can hold 2.82 liters. The cylinder can hold 2.82 liters of water at NTP. I'll repeat the statement again. So the cylinder can hold 2.82 liters of water at NTP. Okay. Now the question is, calculate the number of balloons. Calculate the number of balloons that can be filled up. Calculate the number of balloons that can be filled up. Okay. Now before you start the question, let me tell you what is NTP, people. NTP is normal temperature and pressure. Normal temperature and pressure. Okay. It is very, very similar to STP only. Right. So now normal temperature, NT, normal temperature is again 0 degrees Celsius, but normal pressure is different. I know STP. STP, standard temperature 0 degrees Celsius, standard pressure is 1 atmospheric pressure. Right. But here I'm going, normal pressure is 1 bar. That's the only difference here. Okay. And what we have to understand is, if I have 1 mole of, if I write 1 mole of gas, 1 mole of gas at STP, right? I know it will occupy a volume of 22.4 liters, right? But if the same gas, 1 mole of gas at NTP, right, will occupy a volume of 22.7 liters. Okay, now it's very simple. Why is there a minor change? Because I know 1 atm is equal to 1.013 bar, right? Almost equal, right? 1 atm, almost 1, right? This is the conversion, right? So 1 mole of any gas at STP will occupy a volume of 22.4 liters. 1 mole of any gas at NTP will occupy a volume of 22.7 liters. Okay. Now, just giving you a gist of what is asked in the question, people are not going to solve you are only going to solve, just giving you a gist. So there is a balloon, right? There is a balloon and which is connected to a cylinder. Okay, there is a balloon which is connected to a cylinder. Okay, now from this cylinder, the hydrogen gas goes and it is going to fill up this particular balloon. Obviously, the volume of the gas inside this is very high, so that so many such balloons can be filled. Right, the volume of this is so high that not only 1 balloon, so many balloons can be filled, one after the other, one after the other. They're asking you how many balloons can be filled with the help of this container. This much amount of gas is there, this much amount of volume is there, everything is there. How many balloons can be filled by this container is what they're asking. Okay, this is the gist of the question. Now you can try to solve it, and eventually I'm going to help you out. there is something wrong in the question. You try. Guys, change the statement. I told you that the cylinder can hold 2.82 liters of water at NTP, something I told, right? But one
Yes,
second.
sir.
One second. T- T- wait, this 2.82
Sir,
liters.
why is it wrong?
Sorry?
Sir, I guess the answer is coming, sir. It isn't wrong.
The answer is coming?
No, sir. I meant if I calculate further, the answer is going to come, sir. So I don't think it's wrong.
The answer is going to come, but the datas are not clear. I mean, liters at NTP. Okay. When I have 0 degrees Celsius and this much pressure, can go into 72% water.
Sir,
Mm-hmm.
sir, so for converting from Intp to STP, we have to use that formula P1 V1.
You don't have to convert anything, right? Everything is calculated only at NTP.
No, sir, for finding the volume of hydrogen.
For finding the volume of hydrogen in water.
In the cylinder.
In the cylinder, 20 atm, 27 degrees Celsius. No, you don't have to do it. But nowhere STP is asked, right? In the cylinder, they are telling that 2.82 liters of water can be there at NTP, right? But the temperature now the cylinder contains is 20 atm and 27 degrees Celsius. So there is no STP here as such. There is something which has to be given, or I can calculate for H2 gas. So if they say 2.82 liter at NTP, means how much H2 can be there? H2 can be there, STP. Calculate. This much H2 can be there. So that is the volume of H2. 1 mole of any gas. So how many moles is 2.8? Divided by 7 will be the number of moles. The same number of moles of H2. Again, that doesn't make sense, right?
Sir,
Yeah.
is it 10?
Yeah, the answer is 10, yes. Can you tell me the solutions? What did you do? I'll check.
Can I tell, sir? Because I
Yeah,
don't
you
have
can
phone.
tell. Yeah, you can tell, yes.
Sir, first I found volume of one balloon.
Okay.
So volume of n balloons will be n
Into N. Okay.
into n, yes, sir.
Ah,
And it
okay.
is given that the cylinder is already occupying some amount of water. So the volume occupied by H2 gas will, we have to subtract, sir, 4.85.
Like, okay, no. Volume of H2 occupied should be what?
It has to be subtracted
From?
2.82.
Okay. Okay, understood. In the cylinder, the volume of
Yes, sir,
H2.
in the cylinder.
Understood. Okay.
And then we have to use PV by T is equal to constant.
But if you do that, they are telling, see, they are telling that the cylinder containing, from a cylinder containing a gas containing H2 gas at 20 atm and 27 degrees Celsius. Okay.
Yes, sir.
And they're telling that the cylinder can hold 2.82 liters of water at NTP. The cylinder can hold. So it doesn't mean that already the gas is already the cylinder contains 2.8 liters of water. No, it doesn't mean like that, right? They're telling that the cylinder can hold 2.82 liters of water at NTP.
Sir,
Right?
then there is no use of that sentence, sir.
Yeah, that's what even I'm thinking. Why did they even give the statement? How are we going to use this is what I'm thinking. But the answer is correct. What I got is correct. But the way in which they have solved here is a little different from what you have solved. Now, actually, instead of subtracting, they actually added it. Right? They added 2.82 with that whatever the volume plus n, like they added it, and then they got this. The answer is correct. Indeed, the answer is correct. So 2.82 liters of water at NTP. Okay. Now the temperature and pressure are 20 atm and 27 degrees Celsius. So in that, how much H2 can be added? See, this is what I want to know. Okay. See, they're telling that at NTP, right, we can have 2.82 liters of water vapor, obviously, water in the gaseous form. Now, what I want to know is when I have 20 atm, see, when I know NTP means 1 atmospheric, not 1 bar pressure and 0 degrees Celsius, I can have this many liters of 2.8 liters of H2O. Now, if I can find at 20 atm and how much degrees Celsius, that is 300 Kelvin, that is 27 degrees Celsius, right? This is 273 Kelvin. Okay, I want to know how many liters of H2 can be there. If I can find this value, then you are set. That's it. This is all we need to find. Is there any way we'll be able to find this? At NTP, this much volume of H2O at 20 atm and 300 Kelvin, how many liters of H2 should be there if I can calculate? Then the problem is set. I know this is the total volume of H2. Then I know what is the number of volume of N balloons and whatever. I can divide these two and get the answer. Very simple, right?
Oh,
but
sir.
how do, yeah, tell me.
Where do we use the ideal gas equation?
No, in this case, there is no ideal gas equation as such. Ideal gas equation, if you can use here, but everything is different. Like we have to use this P1 V1 by T1 somewhere, right? But if at all you go by this method, whatever I am telling, right? You don't need to use that also. Okay. Now, how do we know that if at all at this much temperature and pressure, this much volume, and this much temperature and pressure, it is not even H2O, it is H2 here. Totally different gases also.
Sir.
Yeah.
Sir, why can't we use the ideal gas equation?
You use ideal gas equation. Why not? There is no restriction here. We can use PV is equal to nRT to find the number of moles here, right? That you can find out. Okay. You can find the number of moles of H2O, which can be there at the cylinder at these conditions, right? After that, what will you do? I don't know what is the number of moles of H2 here. Okay.
Okay, sir. Understood.
But we can do this, right? At NTP, I know any gas, 1 mole of any gas, right, will have a volume of 22.7 liters. That I know. Any gas for that matter. Right? Okay. So if that's the case, whether it is H2O or H2, the number of moles at NTP should be same. Can I say this, people?
Yes, sir.
Again, right? So whatever be the gas, either it's H2O, water vapor, or H2 gas, I can say that whatever be the number of moles of H2O will be the number of moles of H2 also because of the statement coming from here. Right? I can actually do that now, right? So now they have given that it is the volume. Okay, number of moles is what? Number of moles is given volume divided by, in this case, it's NTP, so it is 22.7 liters. So I already know that is 2.82 divided by 22.7 will be the number of moles of H2O. That can be the number of moles of H2 also at NTP. Right? Now what I can do is, now I can connect this. Now I know H2's number of moles also. Right? Now I can actually put this here. I can use P1 V1 by N1 T1 equal to P2 V2 by N2 T2. Okay. Now, if all these are for, now this is for this condition, right? These are the conditions. NTP conditions are for 1, right? And these conditions are for 2, right? So here I can calculate what is the number, but I don't know. Okay, I don't know volume also. Again, no problem. Okay. So, okay, people, I don't want to wait. What is the time? Almost we have wasted half an hour on this, right? Okay, you can go for the break. Okay, we'll meet you after the break, right? And after that, you're going to solve this or not? I don't know, but definitely we'll solve this either today
sir,
or, yeah, tell me.
Sir, could you derive the equation for PV upon T equals constant?
PV upon?
PV upon T is constant.
Oh,
yes,
okay. So that's easy. P is directly proportional to V, right? And we have P is inversely proportional to V, and V is directly proportional to T. So if you combine all that we'll get is PV by T is constant. That's it.
Sir, is it derived from the ideal gas equation? Like
no. These are derived from the individual laws, right? And these individual laws, again, on combining with the Avogadro's laws, from this we get the ideal gas equation. It's not like ideal gas equation, from ideal gas equation we get these laws. No. From all these laws, we get the ideal gas equation.
Sir,
okay. Yeah, tell me.
Sir, in this question, first we can write PV is equal to NIT. Okay. And now, just as he said, the number of moles is going to be same in both, right?
Number of moles is?
Number of moles of water is going to be equal to the number of moles of
H2.
hydrogen gas.
Okay. At NTP. Only at NTP we can say this. Okay, fine.
Yes, sir. So if PV is equal to nRT,
Hmm.
then N into R should be equal to PV by T, correct?
Okay. Okay.
Yes, sir. So we can say like this also, right? In the
Hmm.
sense, the same formula, but then I'm telling since N is constant, so PV by T is also constant.
Sir, how is n constant?
Yeah, like see, definitely in this case, whatever the number of moles of H2 and number of moles of H2 you have at NTP, that will not be same here. You will have a different number of moles at 20 atm and 300 Kelvin. But if at all, if it's a closed container, right? This is a closed container. So whatever be the amount of H2 or H2O you had should be same, because the gas cannot escape unless and until we are connecting it to the balloon, obviously. Right now, this is a closed container. So can I tell that this is the number of moles here also? Actually, I can tell this because this is a closed container. Right? Whatever the number of moles of H2 and H2O we are finding here, that should be the number of moles of H2, which is here also. And if that's the case, I can use ideal gas equation. That is, now you can use these pressures. That is 20 into what is the volume? Volume we have to find, right? Volume of H2 is what we have to find, which is equal to number of moles is what? 2.82 divided by 22.87. Okay. 2.82 divided by 22.7 into N. Okay, this is what is N into R. R value should be 0.0821 into temperature. Temperature is how much? 27 degrees Celsius, that is 300 Kelvin. Right. So guys, quickly tell me, just calculate this in calculator and tell me what is the volume of H2 we are getting quickly.
4.851.
4.851.
4.851. Volume of H2 in balloon.
From these calculations, I'm telling. From these calculations. So volume of H2 should be equal to 2.82 divided by 22.7 into 0.0821 into 300 divided by 20. I want to know what is this entire calculation. Quickly put it in calculator, people. I can also do this. So we have 2.82 into 0.0821 into, that is 300. People, this is 300, okay? Not 30 into 300, okay? Equal to, okay, divided by 22.7.
I'm getting 1.53.
1.5.
1.53. Yeah.
Are we doing the calculation properly?
Sir, you can cross check again, sir.
Yeah. I'm checking. So this 20 will come down and everything is okay. PV is equal to N into R into T. Okay, fine. This is okay. Everything is done. So let me do it again. So we have 2.82 into 0.0821 into 300. Okay. Divided by 22.7 divided by 22.7 equal to divided by 20. Are you getting 1.5 or 0.15?
Sir, it's like before it was 30, no. So now if you take 300, it's 1.53. But
no. If you take 300 only, I'm getting it as 0.1529 something. I'm getting that.
Sir, same answer, but actually it's 1.529, sir. I think you took it as 30 by mistake. Even I did that before.
No, I'm putting it as 300 only. But even if it is 1.5 or 0.15, that doesn't make sense. Because the volume of one balloon itself, I think you're getting it as around 4.851 liters, right? I think it's Raghav. Raghav, you got the volume of one balloon itself as 4.851, right? 4.85 liters, something like that.
Sir, I use just for the volume of sphere formula, sir.
Yeah, what is volume of spheres formula will be 4 by 3
4 by
into
3
pi.
pi r cube. Yes, sir.
Okay. Now that would be 4 by 3 into 22 by 7 into r into r into r. That is 21 by 2 into 21 by 2 into 21 by 2, because 21 is the diameter. So if I do that, let me do this. So we have 4 into 22 into 21 into 21 into 21, right? Okay. Equal to, divided by, this is 4 by 3 is 21, okay, and divided by 2, okay, divided by 2, divided by 2. So yeah, this would be 4851. And what is the, okay, this will be in centimeter cube, right? Because our diameter is given in terms of centimeters. This will be centimeter cube. So that,
Yes, sir.
that is nothing but 4851 ml, which would be 4.851 liters. That is the volume.
Yes, sir.
So guys, I don't want to waste time here. Okay, we have a lot to cover. Let me look into this. Maybe next class I will solve this question. What exactly are they trying to ask? Let me think about it, and we'll solve this. But I don't know how you got the answer correctly, Raghav. The answer is 10. Okay, but the
Sir,
approach
now
which
you can use PB by T is equal to constant formula. So you will get the answer. So now
PV,
you,
we can write
yes, sir.
P1 V1 by T1 equal to P2 V2 by T2. Okay, so what all will substitute here? P1 V1 T1, P1 P2 V2 V2 T2.
20 ATM.
P1 is 20 ATM.
Yes, sir.
Okay, 20 ATM. Volume, what is the volume? We don't know.
2.82. It's given, sir.
2.82. That is a volume
Sir, but
of,
that is for water, right?
yeah, that is for water, and that too at NTP, right? But now from the cylinder, what we are taking is that cylinder is at 20 ATM and 27 degrees Celsius. And we have to calculate for H2 also. Right? That's the thing. That is the thing. Okay. So guys, go for a break. Go for a break. I'll think about this. Okay, and we'll definitely solve this question. Don't worry. I will not be able to sleep like this if at all I don't solve one particular question. Don't worry. I will be solving and I'll let you know. Okay. What is the time? We have 6:09. So we'll meet by 6:20. Okay, 10 minutes break. We'll meet again. Right. I'm going to switch off my video and mute myself. I'll meet you guys at 6:20. Okay. Hi guys. I hope you're back. Hi guys, back. Shall we start? People?
Yes, sir.
Are you there? Okay. Cool. This question I will think about it, as I told, right? I am still thinking about it. Okay. I will, once I get a concrete, like satisfying me kind of solution, I will let you know. Okay. Fine. Your question, next question. Take it down. I think it's problem number 6. At 0 degrees Celsius, the density of a gas X, the density of a gas named X at 2 bar, at 0 degrees Celsius, the density of a gas X at 2 bar is same as that of nitrogen at 7 bar, sorry, 5 bar, right? Same as a nitrogen at 5 bar. Okay, right. Now they're asking, what is the molecular mass? What is the molecular mass of the gas X? What is the molecular mass of the gas X? I'll repeat the question one more time entirely, people. Right? At 0 degrees Celsius, the density of a gas, X at 2 bar is same as that of the nitrogen at 5 bar. Right? They want to know what is the molecular mass of the gas X. That's the question. Go for it.
Sir, is it 35?
What kana?
35.
35. I think you did some mistake. Did you miss a 2 anywhere? Now again, they did not say anything about the temperature. So temperature is same. It's still 0 degrees Celsius for gas X, 0 degrees Celsius for nitrogen. Okay. Right. So it's a very simple formula, I guess. D is equal to PM by RT. This is what we have to use. Right. Okay, so they're telling density. Okay, so we have to equate two things. One is for gas X and another is for the nitrogen gas. Okay.
Sir,
So
what is the atomic mass of nitrogen? Is it 14? 14
20,
right?
28.
Oh, then into 2, sir.
Right. Nitrogen atomic mass is 14, but it's
Okay.
N2 gas. Right?
Oh, so 70 is the answer.
Sorry?
70.
70 is the answer. Yes, correct. Right. So we have P of N2 into the molecular mass of N2 divided by RT is equal to P of the gas X into the molecular mass of gas X divided by R into T. R into T gets cancelled. Right? Okay. So the pressure of N2, they're telling it as 5 bar, and the molecular mass of N2 I know is 28 because we're talking about N2. So that would be the pressure of X is given to be how much? 2 bar. Okay. 2 bar into the molecular mass of X. That's it. So this can be 14 times. So 5 into 14, the molecular mass of X is 70 gram per mole. That's the answer. Very simple question. Okay. Next question. Okay. Next question. Question number 7. What mass of neon neon gas should be introduced? What mass of neon should be introduced into an evacuated vessel? Into an evacuated vessel, what mass of neon or what mass of neon gas should be introduced into an evacuated vessel of volume, 0.88 liters, 0.88 liters, to produce a pressure of 90 kilopascal, to produce a pressure of 90 kilopascal at 30 degrees Celsius. At 30 degrees Celsius.
Sir, are all the noble gases monoatomic?
Yeah, monatomic. All of the noble gases are monatomic. Yes. Okay.
And all the halogens are diatomic.
Yeah, all the halogens, all non-metals gases are generally diatomic, except for phosphorus and sulfur. Sulfur will be S8, phosphorus
okay,
will be P4.
Okay, sir.
Okay. So I'll repeat the question one more time, people. What mass of neon gas should be introduced into an evacuated vessel of volume 0.88 liters to produce a pressure of 90 kilopascal at 30 degrees Celsius? Okay. Right. So this is obviously from ideal gas equation. There is no other way. Right. This is obviously from ideal gas equation. Guys, what will be the R value you will use here? What is the R value you guys will use here in this question?
Sir, 8.313.
Yes.
314.
Whenever we go for SI units, Pascal is an SI unit, right? Whenever you go for SI unit, R value should be, remember that, pressure in ATM, volume in liters, then R value is 0.0821. 0821. Okay. 0.0821. If pressure is in Pascal and volume is in liter or meter cube, okay, meter cube, we go for generally, not exactly meter cube, we can have liters. Okay, it's all about pressure, or what pressure you're doing it. Now, in that case, you have to use the R value as 8.314. Okay. So in this case, you have to use the value as value of R as 8.314. Be very careful.
So you can use calculator, right?
This side or this side?
No, sir, I'm asking you can use calculator, right?
No. You cannot. Here, if I let you use, you can use, not a big deal. But again, in your exams, you will not be using that. So it's better to calculate by yourself.
Sir, it will come around
Sir.
600 something.
Sir, 620. I'm getting 628.
628.
I'm getting
I think
662.
what you are getting?
662.
662. Okay. I don't know whether did you guys miss any 100 somewhere? Check it. But 628. See, both answers are wrong. Okay, but 628, I can understand that somewhere you missed 100. Right? It is a little closer. Kilopascal, guys, did you put 10 to the power 3?
Yes, sir.
Yes, sir.
Okay. Volume is 0.888 liters. Anything else? Should be fine. Okay. So I just idealize equation only. We'll check. Okay, PV equal to nRT. So what we have to find? Okay, we have to
Oh
find
no,
the.
sir. Sorry. I put like 9,000, sir, by mistake. 90,000.
Okay, guys, there is a small thing which we have to understand. Okay, it is my mistake. It is not your mistake. Okay, so what you have to understand is if pressure is in Pascal and if volume is in meter cube, then we use 8.314. Okay, or in other words, I can tell it like this: if I have kilopascal and liters, then I can directly use 8.314. Okay, these are all the things you have to understand. There's a small thing because I know 1000 liters is what is 1 meter cube, right? So that adjustment can be done here. Okay, so all that you have to understand is ATM and liters 0.0821, Pascal and meter cube, then 8.314, and if they give you in kilopascal and liters, then again 8.314. Okay, I think that is where the mistake lies. Right, it is my mistake, not your mistake. Right, everything else is right. So you don't have to convert kilopascal into Pascal and then do this. You can just directly take the kilopascal value and put the R value as 8.314. Now, because this particular thing, this should be in meter cube, SI units, then only this is an 8.314. Now, I know they are given it in liters. Okay, so eventually it will become 1000 liters and stuff, everything will change. Or you can even write it as, if they give you in kilopascal as pressure and volume in liters, then it is going to be 8.314. Okay, this is another thing which you can note. Okay, so directly you can substitute here. Pressure is 90 kilopascal. You can just keep it as kilopascal. Into volume is 0.88. Into number of moles is we don't know. Okay, so we have what gas are we talking about? Neon, right? Okay, so the mass, given mass divided by molecular mass. Molecular mass is 20 here for neon.
Yes, sir.
Okay, 20. Okay, molecular mass of neon is 20. Into R, L value is 8.314. And the temperature is given as 30 degrees Celsius, that is 303 Kelvin. Okay, so you will get the mass of this thing to be almost 0.63 grams. Okay, so what you did was correct. It was my mistake only, my bad. Okay, the answer should be 0.63 grams. Okay, right?
Sir,
Yeah.
how do we know that it's grams?
How do we know that it's in grams? Oh, that's fine, right? Because this is in grams only, no issues. We always write it like this is number of moles. How do we write this? This is gram and this is in gram per mole. So when we gram gets cancelled, we get mole. That is always going to be in mole, grams only. Okay, whatever the answer you'll get will be in grams only, no issues at all. Next question.
Sir, are there any other units of P and V except these?
Yeah, we have. Actually, let me give you this. Okay. Right, I'll send you a picture, but whom should I send is the question. Or I'll let me paste it here so that you can take a screenshot or something. Wait. But, okay, wait. Where are you? 1 second, guys.
Sir, you can send it to me. I'll send it immediately in the group.
No. 1 second. I'll just put it in the. So, do you guys have a group or something? Guys, do you have some group or something or for yourself?
Sure,
All of you are there.
Epsilon group, not.
Okay. So then I'm not there in the group. Can you just send me a hi, Suprajit? I'll just send you there.
Okay, sir.
Yeah. So these are all the different units. You can just put it in the group also and let everybody see.
I've put it, sir.
Yeah, good. Right, these are all the possible units of R. Okay. Fine. Next question. 8th question. Okay, take down 3.7 grams of a gas, 3.7 grams of or wait, this seems like an interesting question. 0.553 seems interesting. We'll take this question. Rab, like strike out whatever you wrote, people. Right. A boron hydride. A boron hydride BXHY. Okay, a boron hydride BXHY has 85.7% boron. Okay, has 87.5% of boron. Full stop. 0.553 grams of this compound, 0.553 grams of this compound occupied 0.553 grams of this compound occupied 407 ml at 373 degrees Celsius, sorry, 373 Kelvin. It occupied 407 ml at 373 Kelvin and 0.658 atm pressure. Okay, right. Now I want you to find.
Sir, could you repeat the pressure?
Yeah, I'll repeat. You have to find X and Y. Okay, calculate X and Y is what you have to find. This X and Y is what you have to calculate. Okay, so let me repeat the question one more time, people. A boron hydride BXHY has 85.7% boron in it. Full stop. Right. Now, next statement says 0.553 grams of this compound, that is BXHY, right, occupies 407 ml at 373 Kelvin and 0.658 atm. Okay, this is the pressure, this is the volume, this is the pressure, this is the temperature, and at that temperature, this many grams of the compound occupies 407 ml. Right? So they're asking you to find the molecular formula. Basically, they have to find what? X and Y. That's what they have to find. Okay, go for it. Interesting question. And for this question, you can use calculators.
So 407 ml or
407 ml at 373 Kelvin and 0.658 atm. You can use calculators for this question, guys, because I know the calculations are a little difficult here, and we have to save time also, right? So you can use calculators.
Sir, is it compulsory to convert into liters while using ideal gas equation?
Yeah, obviously. Yes. Because if you just put 407 and if you use R value as 0.0821, it is wrong. You have to convert it to liters because the R value is in terms of liter atmosphere, not ml atmosphere, right? Is use the molecular atomic mass of boron to be 11. Actual value is 10.8. Okay, 10.8 is the actual value, but you can use plus 11. But since you're using calculators, why not use 10.8 only? Okay, atomic mass of boron is 10.8. So guys, you'll be writing a test on this particular chapter, states of matter, on 31st of December. Okay, by next week I'll be completing this chapter. Mostly by Saturday itself I'll be completing this chapter. Okay, and you'll be getting your assignments also. You'll have 1 week's time to do your assignments, and after the 1 week is over, directly you'll go for the test.
So what was the atomic mass of boron which you told?
10.8. You have to use this 10.8.
Sir, is it B5H9?
Yeah, correct. Okay, maybe I'll give you 1 more minute for anybody else to get the correct answer. I actually see a lot of difference. People who are very strong, like generally, like what to say, this actually happens for even me, right? I feel that I am very strong in organic, right? I'm comparatively not so strong in inorganic. Inorganic also is okay. Inorganic also can be managed, but physical, yeah, like compared to organic is less, right? So like that, I think everybody has that thing, right? I feel that certain students are very strong in organic, certain students are very strong in physical, right? I actually see that there is a difference. Okay, perfect. Anybody else got B5H9? Okay.
Sir, can you give 1 more minute?
1 more minute? Okay, fine.
Yes, sir, I'm getting the same answer.
B5H9. Okay, good. Okay, so people, what do you have to do? Again, we have to use this PV is equal to nRT only, right? So see, understand, somehow we have to find this X and Y, right? So if I can know at least the molecular mass of this compound, if I can just find the molecular mass of the compound, something I'll be able to work it out. Okay, so the first step in this question is to find the molecular mass of BXHY, right? And that can be easily found out with the help of this equation, PV is equal to nRT. So let us rewrite this equation, and number of moles is given mass by the molecular mass into R into T. Let us substitute the values. Pressure is 0.658 atm, volume is 0.407 liters. It's 407 ml, but I should write it as 0.407 liters. Should be equal to given mass. Okay, given mass is known. How much? 0.553. That is the given mass. Divided by the molecular mass of the compound, which I don't know, into R value is 0.0821, into temperature is how much? 373 Kelvin. Okay. Now I know that the calculation is very easy, very difficult. That's why I asked you to use the calculators. You will find the molecular mass of the compound to be 63.23 gram per mole. That is the molecular mass of the compound.
It's 6.3.
Okay. What?
6.3.
6.
No, sir. No, sir. 63 only, sir. 63.2361. Exactly.
Yeah, 63.23 gram per mole is only you should be getting. Okay. Right. Now, we understood that boron in this BXHY, they said that 85.7% is boron. That means what? This is the total weight. This is the total weight. In that, 85.7% is boron. So can I tell that 85.7% of 63.23 of 62.23 will be the mass of boron? Will be the mass of boron only. Okay, that I can easily do. How do we do this? 85.7 divided by 100 into 63.23. That will be the mass of boron, right? Because they are given 87.5% of this compound is only boron, right? So if this is the molecular mass, 85.7% of this mass is going to be the mass of boron, and that value you should have
53.75
grams. Okay, 54.19 grams, and that's it, right? Now, if you have 54.19 grams of boron, can you calculate how many borons will be there? Say, though I'm calculating the number of the borons, right? Number of borons would be 54.19 divided by what is the mass of boron? Atomic mass of boron is 10.8, right? So this approximately you should be getting it as 5. Okay, so X we got 5. Done. Right now, how do you calculate Y? That is for hydrogen, right? So out of this 62.23, this much is the this much is the value of a value for boron. Okay, this much is the value for boron, right? So I can write it like this: 54.19 plus y number of hydrogen atoms are there, and each of the hydrogen atom will have a mass of 1 gram per 1 gram, right? And that totally should be equal to what? That totally should be equal to the total mass, right? So you will find out the y value to be 9.23, approximately 9.23. But again, if you want to calculate the number of hydrogen molecules, now that would be given mass. This is grams, 9.23 grams divided by 1 gram. That is nothing but approximately, you don't get the whole number, right? So approximately you will get it as 9, right? So y value is 9. So what should be the formula of the compound? B5H. Very, very simple. Okay, so I just repeat it one more time, people. Right, so this is very easy. Calculation of molecular mass from PV is equal to nRT is very easy. Once you do that, this is like what this means. If 1 mole of BXHY, 1 mole of BXHY will have this many mass, this much mass. Okay, fine. Now they say that 85.7% of this compound is boron. So 85.7% of this weight should be equal to the mass of boron, right? And that we calculated, to be 54.19. And you have to find the number of boron atoms here, right? This many mass, this is the mass divided by the atomic mass of boron will give you approximately 5. So we got X is equal to 5, right? Now we have known that total mass is 63.23. Out of the 54.19 is the mass of boron, right? So the rest mass, that is 9.23 grams, is the mass of hydrogen, right? Then again you can find the number of moles of hydrogen. That would be this divided by 1, approximately again 9. The whole number is what you have to get. Right? We cannot write it as B5H 9.23. That doesn't make sense. So it should be B5H9. That's the answer to this question. Okay. So this looks tricky, but it's actually very, very simple. Very, very simple.
Sir?
Okay. Yeah, tell me.
Sir, actually, I got an error in the calculation, but then still I got boron 0.5 and hydrogen 0.9. So then I converted into simplest whole number, and still I got the same answer.
What did you miss? I don't know. Check your calculations.
So instead of 63, I wrote 6.3, and instead of 9.2, I wrote 0.9.
Yeah. But okay, that makes sense. I think this is the mistake. This is in the PV is equal to nRT only. You have done some mistake. Check
Yes,
it
sir.
out. Okay, but whatever the number you will get, other than that, here everything is going to be same. Like, I mean, if at all you get only point difference, that doesn't make any difference in 5, and the ratio is basically X is to Y. That ratio will not change. Yes, that's true.
Sir.
Yeah, tell me.
Sir, that 54.19, I'm getting 53.75, sir. So we can approximate it to
approximately you should be getting 5. No matter, no problem at all.
Okay, sir.
Right? Doesn't matter. Okay, people. Okay. So what is the time we have? 55. Can I continue, or I think we can see tomorrow? I think we can see tomorrow, guys. Okay. We'll see you again tomorrow. Okay. Let us stop with this for today. So that's it. The problem that this entire 2 hours was used for problems, but I know half an hour was wasted in tackling that particular question, and that is still there in my mind. Right? I'll think about it, okay, and let you know what exactly it is. Or I don't even know whether the question is correct or not. Let me maybe discuss with my colleagues. Like first, I will try. If I'm not able to, let me discuss with my colleagues and let you know. Okay. Right. Fine, people. Thank you so much. It was a very nice class. Thank you so much. We'll meet again.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you, everybody.